Welcome to our mini-series on measurement-based quantum computation. Today is part 2 on fault tolerance. Okay, so this is what it's like. Just look at the picture. If it's not quite so clear what this picture is supposed to tell you, don't worry, we will get to that through this lecture. At the end of this lecture, I promise you, you will understand it. For now, maybe two things to say. When we go from universality to fault tolerance, while of course keeping universality, we move from two-dimensional cluster states to three-dimensional cluster states. That gives us the fault tolerance in addition. And if you think of making the cluster states by the Ising interaction, for example, then it's also noteworthy that you only need translation short-range Ising interaction. Okay, so another aspect relating to the figure that you just saw is how to explain quantum gates. So this braiding of strands represents a CNOT gate, and we will also explain what this means. Okay, so here is an outline of this lecture. There's only 2 items on the menu, so we will talk about how to do error correction in three-dimensional cluster states and how to do fault-tolerant gates in cluster states. All right, so let's begin with a little bit of a recap in quantum error correction. Not very much at all, just the most essential things. So here is what fault tolerance is good for overall. We know that decoherence is troublesome for a quantum computer. It takes the state of the quantum register towards the classical regime, and so the computational power, the added computational power of a quantum computer disappears. So you want prevent decoherence from occurring. And how do you do that? Well, that is what quantum error correction does for you. So there are software techniques for overcoming decoherence. And the central result in this realm is the threshold theorem. The threshold theorem says that if every gate in your quantum circuit, or in our case, it will be measurements, the error for every individual operation in your quantum computation is below a critical level. That critical level is called the error threshold or decoherence threshold. So if the amount of decoherence is below that threshold, then you can compute arbitrarily long and arbitrarily accurate. So it's almost as if no errors were there. I hope that you will all have a background in fault tolerance, and if that's not the case, you can look at Huy Nguyen's lecture on quantum error correction here in this series, or you may just read the Nielsen and Schwang. I mean, you don't even need to read the whole book, it's all in chapter 10, if you are so inclined. Okay, so I'm assuming you know something about quantum error correction. So let me just recap the basics so that we are all on the same page. So quantum error correction uses quantum codes, and quantum codes are twins of classical codes. So in a way, quantum error correction can be regarded as 2 copies of classical error correction running in parallel. So let me explain this just for the simple example of the 3-qubit repetition code. 3-qubit repetition code is not a good quantum code at all. It's a terrible quantum code, in fact, but it's good for explaining things. So let's look at that here. So let's look at the dictionary. The dictionary is the thing we want to establish, or we want to review it rather. So repetition code is also a classical code, so it has 2 code words, the encoded 0 and the encoded 1. And the encoded 0 is just a bunch of zeros repeated. The encoded 1 is just a bunch of ones repeated. Okay, the quantum code is just this in superposition. So you now have a cat corresponding to the encoded 0, and you have another cat corresponding to the encoded 1. And they come now with arbitrary amplitudes. So this is what the encoded states look like. You have 1 qubit encoded in 3. So, well, this is decoherence, so you have errors. Classically, your errors are bit flips, just bit flips. Quantum mechanically, you can have two types of errors. You can have spin flips and phase flips and their combination. So Pauli flips sigma x, sigma y, and sigma z. In the classical code, and not just this repetition code, any linear code, you have a parity check matrix that tells you about possible errors. Quantum mechanically, the rows of the parity check matrix correspond to the stabilizer operators. So in case, let's begin with the classical code. When we look at these code words, we see that the first and the second bit have to agree, and the, say, second and the third bit have to agree. And that is what you see reflected in the rows of the parity check matrix. On the quantum side, we find it's in direct correspondence that when you apply the Pauli phase flip operator sigma z on qubit 1 times sigma z on qubit 2 to any encoded state, you find that any encoded state is an eigenstate of that operator with eigenvalue 1, any state in that code space. So when you measure this observable, you are expected to find outcome +1. And when you don't get that, then you know that an error must have happened, and you can then try to figure out what that error is. So that clarifies the error correction part. And it is now one more thing I would like to say. One other thing is important. When you do these measurements, the measurement of these stabilizer operators, you do not learn what the encoded state was. So you leave that quantum information untouched. Yeah, so there's two things you want to do. You want to learn about errors, but you do not want to learn anything about the quantum information processed. Okay, so let's summarize what we do in quantum error correction. We repeatedly measure the stabilizer operators, and from their outcomes, the syndrome, we try to infer what the error was. And so errors we can detect and correct, they will anti-commute with some of the stabilizer operators. This is how we find them in the syndrome. Okay, so let's now, from these details, and of course it was very short for the details that are there, but now let's zoom out again. And this gets us back to the threshold theorem. So we said quantum error correction requires an encoding. And what we will see, I mean, we could have elaborated this for the 3-qubit repetition code. It's a very small code. We cannot correct for all errors. There will always be ways to misinterpret the syndrome. Then we will not correct for the error that really happened, but some other error that we find more likely. And by doing so, we introduce an error on the logical level. So the upshot of all of this is, what we can do with error correction is to suppress error, not to eliminate error altogether. And when we make codes larger and larger and larger, then we find that this error suppression will work better and better and better until a certain point when the situation flips over, and then error correction only makes things worse. So when the codes are small, this transition from error correction working to failing is rather smooth. It's a curve like that. But the larger the codes become, in the thermodynamic limit, the function for the residual logical error will become a step function. It will approach constant zero below the threshold and then shoots up and gets you to a completely depolarized scenario for high physical error rates. So, and this step in the step function, that's called the error threshold. So this is intuitively where the threshold theorem comes from. Now comes fault tolerance of cluster state quantum computation. Okay, here is an outline for this section. So there is a few remarks to make before we can even begin. This is just general remarks and getting a little bit technical as we go along. And then the main discussion will have two parts. And these are how to do quantum error correction with three-dimensional cluster states. That is the second part in these four overall. and then how to do fault-tolerant gates. So these are the main ideas that I would like to convey. And then, of course, we have to clean it up. We will have to talk about what the fault tolerance threshold is that results from this and how the operational overhead scales and so on and so forth. Okay, so that's the menu. The fault tolerance part of this mini-series is actually split up into 2 lectures. So here in this first lecture, we will go up to the point of explaining topological error correction with cluster state. So this is point 2.2 here. And with the topological quantum gates and the characteristics of the scheme, we deal in the next lecture. Okay, so we are beginning with the remarks. So here's the first. The fault tolerance threshold that we are going to get out of this is pretty high. So when we go for threshold values, we may want to treat 2 settings separately. There is the setting without any geometric constraints, and there are the settings with geometric constraints. If there is no geometric constraint present, you have more things to do. And the highest threshold that was established in this setting is by Manny Knill for the paper from 2005, and it's a 3% error threshold. So that's the best that is presently known. In our case, the fault tolerance threshold will be about 0.7%, and so that's the highest known for settings with geometrical constraints. And so this applies to dimension 2 and 3. I will explain the 3-dimensional version first. That's the measurement-based version, but then there is a mapping to the circuit model, and that lives in 2 dimensions, 1 dimension lower. Okay, bottom line for this slide, the scheme that comes out of this discussion is actually of practical value. It has a very high error threshold. So this slide is to explain to you what you have learned about quantum error correction in the circuit model relates to error correction here in measurement-based quantum computation. So let's recall what the goal is. So what you have in this setting now is measurement-based quantum computation on a noisy cluster state with imperfect measurements. And using the tools of quantum error correction, what you want to do with this is to simulate measurement-based quantum computation on a perfect cluster state by perfect measurements. So that's the goal. So compare this to the circuit model. In the circuit model, what you want to do is have an encoded quantum register that is noisy and is acted upon by noisy encoded gates and stabilizer measurements. And with that, you want to simulate a quantum register that is noise-free or nearly so and acted upon by noise-free gates. So you see, it is very similar, but it's slightly different. So our setting, to repeat, is to simulate measurement-based quantum computation on a perfect resource state with perfect measurements. And we want to do all of this with noisy states and operations. Good. So now to the main idea. So there's 2 main ideas that go into this scheme. So the first is that 3-dimensional cluster states are a fault-tolerant substrate. So they have quantum error correction built in a way. And that's what we want to talk about. That's the first idea. The second idea is that if you drill holes into the cluster state, that allows you to do encoded gates. And that's also something, of course, we want to talk about here. So these are the main ideas that go into the construction. Okay, so now we come back to this funny picture again, and now we begin to talk about it in more detail. So overall, what you see here is a 3-dimensional slab of cluster state. And then you have these various topologically entangled structures inside. So you have these blue rings and these black rings or dark gray rings, and they hold these red beads in place. These are very special locations. Okay, and those we want to now talk about. So there's, in principle, three regions in the cluster state. There is the region V for vacuum, and it fills most of the cluster. There are these line-like or ring-like regions that are shown in blue and black. They are called defects. And then finally, these rings hold in place these singular qubits, we call them, shown in red. And only when we add these singular qubits, the blue and gray or black structures are actually rings. So they are needed to complete the rings. So the qubits in these three respective regions are measured in specific bases. And that's what distinguishes these regions. And they have a different purpose also. Let's talk about the measurement bases in these regions and the purpose of the belonging qubits. So the qubits in the region V, they are measured in the eigenbasis of X. So that's what's done there. And this region is there to establish the fault tolerance of this computational scheme, or most of it anyway. There's a small correction to be made involving the singular qubits, but we'll get to that in time. So that was the region V. So now the defects, the region D. Every cluster qubit inside such a region is measured in the eigenbasis of sigma z. And as we know in cluster states, the effect of this is to remove all these structures from the cluster. So our 3D cluster state becomes a cheese, in a way. Okay. So also, these defects have two colors. They appear in two colors, and there's a reason for that. So these defects are called primal and dual, and that has to do with the boundary conditions that we create when we make these defects. So if you're familiar with the surface code, you know about different of boundary conditions that can be created. They would be called rough and smooth in case of the surface code, and that's exactly the same situation we face here. And this is only to mention this for the first time. We'll get to that in more detail. Okay, remember the qubits in the D region, the defects, are measured in the eigenbasis of sigma z. Finally, we have the singular qubits. So while the other regions are extended, the singular qubits are now individual qubits held in specific locations by the defects. The purpose of these qubits is to implement the non-Clifford gates. So the qubits in the region D implement the Clifford gates, and the singular qubits implement the non-Clifford gates. So that's what their purpose is. This was a lot of information on this slide. Maybe later in the video you'll come back to it. You will find the uses of what I just said when we go to explaining gate function and fault tolerance. Yeah, so I will refer to this slide a lot. Okay, so now let's look at the cluster microscopically. So previously we had the macroscopic picture, the view from a distance. Now we look at the small scale. In fact, what we are looking at here is an elementary cell of the three-dimensional cluster. So the cluster state as a whole, or its lattice, is the cell that you see here repeated over and over again in all three spatial dimensions. So now that I said that, let's look at the cell itself. So it has faces, edges, sides, and a volume in the middle. So where do the qubits live? The qubit, there's two types of qubits. One type of qubits lives on the edges, and one type lives in the center of the faces. And nearest neighboring qubits, so edge and face, they are connected by a link, and that link corresponds to a conditional phase gate that is used to create the cluster state, or equivalently, it's an edge for the Ising interaction to act on. Yeah. So these Ising interactions, they only occur between nearest neighboring qubits. So qubits on the edges and on the faces, none in the center of the cell, and none on the sides. Okay, duality transformation. So this is something else. to be aware of, and I will get back to it later. Maybe I'll ask you a question about that. Okay, but anyway, what is this duality transformation? So we observe that if we translate the entire three-dimensional cluster state by half a lattice cell in either spatial direction, then we are mapping the cluster state to itself. So maybe you take a moment, you stop the video, take a moment for yourself to verify that property. Okay, so by this translation, the lattice is mapped to itself. However, the cell structure that we came up with is not mapped into itself. So a site becomes a volume, an edge becomes a face. So the cell structure changes. And that is also going to be important. So we can describe one and the same cluster state by a primal lattice, or alternatively, and just as well, by a dual lattice. All right then, so let's talk about quantum error correction in three-dimensional cluster states. Yeah, so here is a thing to try. So remember, this is about protecting the measurement on cluster states. So we want to, with all our error correction techniques, we want to simulate perfect measurements on a perfect cluster state. But of course, neither the measurements nor the cluster states are perfect. Okay, so we want to get syndrome information like we are used to in quantum error correction. So let's try the simplest thing. So what you see here in this picture is the elementary cell and the cluster state stabilizer living on that cell, being supported on that cell. So yeah, so the cluster state stabilizer, it has the form that we learned it has. It has a sigma x in the center and then sigma z's on all the neighboring qubits. So we could just measure that, and through local measurements as required in measurement-based quantum computation, then process these measurement outcomes. They would individually be random, but they are supposed to be correlated in a positive fashion. So from the correlation, you would expect to read off the stabilizer eigenvalue +1. But this may not always happen because errors occur, and that's actually okay. So, but there's something wrong with this method. And remember the slide that I talked about so long with all these entangled defects and so on and so forth. And so the reason that that doesn't work is that the region V in which this all plays out, in this region, the cluster qubits are measured in the eigenbasis of sigma x. So we cannot measure this thing because it had Pauli's operators sigma z. So that thing we cannot measure. So what can we measure? And the criterion is this. So the stabilizer operator has to be a tensor product of Pauli operator sigma x and identity. So that's our criterion. So now the question is, are there such stabilizer elements, and if so, how many, and what do they look like? Okay, and this is what we see here. So we have fairly localized stabilizer operators that are precisely of the required form, sigma x's and identity only. So how do they come about? So the stabilizer element that you see here is the six-fold product of stabilizer generators, namely of the stabilizer generators that are associated with the six faces of the elementary cell. Yeah, one in the front, one in the back, two on the sides, top and bottom. If you multiply these six stabilizer generators together, well, that gives you still a stabilizer element, and what you realize is that the sigma z's all cancel out. So for example, look at the top face and the front face. It has a common edge on which a qubit sits. It has a sigma z from the top stabilizer acting and another sigma z from the front stabilizer acting and nothing else. And so the two sigma z's cancel. And the same happens on all the 12 edges of this elementary cell. Okay, so to summarize, you have a stabilizer element that consists of Pauli operators sigma X only, and this is now something that you can measure by X measurements, as is required in the cluster region V. Yeah? So again, every measurement outcome is random, but they are supposed to be perfectly positively correlated. So when you multiply all the eigenvalues that you measured, you expect to find eigenvalue +1. If you don't, then an error must have occurred. So to summarize this a little bit further, so we are getting 1 bit of syndrome for every cell of our lattice. Still, we need a little bit more to identify errors, and that is what you see here in this picture. Here you see 2 neighboring cells and an error in the middle, between them, on the face in the middle. And this error will show up in the left cell and in the right cell. And so, you can identify this particular error by its syndrome. Not every error will have a different syndrome. There is a lot of errors that have the same syndrome in this case, like in the Tory code, but mostly the difference is harmless. Mostly, even though as physical operations the errors aren't the same, they have the same effect on the code space. This is only not the case when the errors become very, very long-ranged. Okay, so in sum, the error correction that you get with three-dimensional cluster states is one error correction that you already know. It is familiar to you from the Tory code. Namely, when you consider the Tory code with both memory errors and measurement errors, then you get precisely the same error correction method that you're getting here in three-dimensional cluster states. So there's nothing new here in terms of error correction. It is already known. Specifically, what you will be using when correcting errors in three-dimensional cluster state is minimum weight chain matching. And that is an algorithm that has been described a very long time ago.